Hi there. In this video, we're going to be talking about Green's theorem. So let's begin by writing what Green's theorem actually is. If we have some kind of vector f that's acting in the 2D xy plane, and it's made up of components p in the x direction and q in the y direction, and p and q are both functions of x and y, then Green's theorem says that if we take a double integral of some region in the xy plane of dq dx minus dp dy, of course with respect to dx and dy, if we find this integral, we'll see that it's the same of taking the line integral around a closed path of p dx plus q dy. So we'll illustrate this theorem in an example just now, but before we do that, it's important to note that this Green's theorem is actually exactly the same as Stoke's theorem. So I just want to write that down. So Green's theorem is the same as Stoke's theorem. So if we take Stoke's theorem and apply it to the 2D case in the xy plane, so I'll just write that, it's the 2D case in the xy plane, then we actually get Green's theorem. So this might seem a bit strange. So if you want to review Stoke's theorem, you can actually go to the previous video in this lecture series, and you can see what Stoke's theorem is. But just a quick reminder, Stoke's theorem says that if you take the surface integral around some surface of the curl of some vector, and as I mentioned, it's a surface integral, if we do that, we find that it's the same as taking the line integral around a closed path in that region. So that was what Stoke's theorem was. So how does this Stoke's theorem with this curl and all of these things end up looking like Green's theorem, end up looking like what we have just written? So it's quite simple. We would just remember that our vector that's acting in the xy plane is pi plus qj. So let's try and evaluate what the curl of this vector is. And you would recall, if you take the curl of a vector, the way we go about doing it is we firstly put I, j, and k in the first row, day x, day y, and day z in the second row, and in the third row we put the components of our vector, which in this case is p and q. So that's p, q, and you can see that there's no k component, so that becomes 0, and we compute the determinant of this. When we do that, the first term is I, we block out the first column and the first row, so we're taking day y of 0, which is just 0, minus day z of q, so that's day q day z, and then the second term is minus j, we block out the first row and second column, so we find day x of 0, which is just 0, then minus day z of p, so that's day p day z, and lastly, in the direction of the z, in the z direction, we block out the first row and the third column, so we're finding day x of q, that's day q day x, minus day y of p, that's day p day y. And you would see that there is no z component. There is no z component in our vector. So everything with respect to z is actually 0. This term is 0, that term is 0, and what we're left with is day q day x minus day p day y in the k direction. And you will see that in Stoke's theorem, we're taking the dot product with this vector area. And I mentioned several times already that we're considering the case of two-dimensional in the xy plane. So let's look at what the vector area in the xy plane is. So we'll just draw our 3D coordinate system. So we have x, y, and z. So what's happening is that we're considering some region in the xy plane, and we're considering a differential element dx, dy in the xy plane. And you would remember that in any region, we're choosing a anti-clockwise direction, and the vector area has to have a normal vector. So it's the surface vector area. It consists of the surface area element multiplied by the normal vector. So in this particular case, you can see that, okay, we take an anti-clockwise direction like that of our region, and our normal vector is actually in the z direction. So it's just k. So our area element is just dx dy. And we multiply by that normal vector, which is k. So for Stoke's theorem, in the left-hand side of the equation, which I will just refer to quickly. So we see that for Stoke's theorem, what we have to do is we take the curl of the vector and multiply it by the vector area ds. So let's do that. So we saw that the curl of that vector was dq dx minus dp dy, and then we're multiplying now by the vector area. So the curl of the vector f dot product with the vector area is equal to dq dx, that's dq dx minus dp dy, k, and we take the dot product with this vector area ds. That's dx dy times k. And of course, since we're taking the dot product, k times k is just 1. And what we're left with is just dq dx minus dp dy. And of course, dx dy. And Stoke's theorem asks that we take the surface integral, so we integrate this on the left-hand side across some kind of surface. So what that corresponds to is taking the double integral of some region in the xy plane of this integral. And you can see that this actually corresponds to the left-hand side of Green's theorem. So our result says that we're taking the double integral across some region of dq dx minus dp dy in the xy plane. And if we go back up now to what we had written, which is what Green's theorem was, we can see that we had written Green's theorem here, and we have now showed that the left-hand side of Stoke's theorem is actually the same as the left-hand side of Green's theorem. So we can just do that for the right-hand side as well. So the right-hand side of Stoke's theorem essentially was saying that we take the line integral of f dr, and f we know is made up of the components of pi plus qj, and dr we know is just dxi plus dyj, and if we multiply all of these things, I times I gives us 1 as we're taking the dot product. So what we get is the line integral around the closed path of pdx plus qdy, and which we see is actually the right-hand side of Green's theorem. So let's just illustrate Green's theorem in a basic example, just to show via the example that it is actually true, even though we know that Stoke's theorem is true. And if Stoke's theorem becomes Green theorem in the xy plane, then it should be the same. So that is as expected. So once more, what is Green's theorem? It is the double integral of some region of dq dx minus dp dy dx dy, and that is the same as taking the line integral around the closed path of p dx plus q dy. So our simple example will just consist of a closed path bounded by two curves in the xy plane. So that's our xy plane and our two curves. So we'll say that the path, something goes from the path of 0 to 1. So we'll call this P, and its coordinates is 1, 1. So something travels from the point of origin to P and then goes back from P back to this point of origin along some other curve. So we'll call this first path C1, or the first part of the curve C1, and the other one going back to the origin C2. So this bottom curve, we'll just call it y is equal to x squared. And the other part of the curve, we'll say that y is equal to the square root of x. So this is the path traveled along by something, whatever it may be. And this is the region that's bounded by these two curves. And we want to apply Green's theorem to this scenario. And we want to show that this left-hand side of Green's theorem is the same as the right-hand side. So acting along this curve is the vector f, and we'll say that, of course, f has the form pi plus qj. So the x component of f is xy, and the y component of f is 2x minus y. Of course, j indicates the y direction. So let's start by applying it to the left-hand side. So the left-hand side, we'll just evaluate this double integral. So we can see that we need day q dx and day p dy. So this is q and that's p. So we can begin. We're taking the double integral around this region, so we can actually write the boundaries of this region. We can just take a thin strip. We take a thin strip like that. And we're integrating from y is equal to x squared. So we're integrating from x squared all the way to the square root of x, which is the top curve. So we're going from x squared to the square root of x. And in the x direction, we're going from 0 to 1. So we're integrating these strips from 0 to 1. So now that we have our boundaries of integration, we can actually proceed to evaluate this integral. So the first term requires a derivative of q with respect to x. So that's p and that's q. And the derivative of q with respect to x. So we can see that this is just 2. Derivative of y is going to be 0 since we're taking with respect to x. And of course, derivative of 2x is just 2. So that's 2. And now we need derivative of p with respect to y. So that's just going to give us x. And our order of integration is we're integrating with respect to y first, and then with respect to x. X goes from 0 to 1, the outer integral. So when we do that, we get the integral from 0 to 1, 2y minus xy, and that's going from x squared to the square root of x dx. And when we substitute that in, we get integral from 0 to 1, putting in x to the power half. Square root of x is x to the power half. We put that in here, so we get 2x to the power half minus x to the power 3 over 2. So x to the power half, so we have x times x to the power half. 1 plus a half is 3 over 2, which we can see. And then minus 2x squared. So substituting in x squared. And lastly, plus x cubed. A minus and a minus gives you a plus, so that's the plus that you see. And x squared times x gives us x cubed. So all we now need to do is integrate this with respect to x. And when we do that, the integral of x to the power half is x to the power 3 over 2. And 3 over 2 times something must give us 2. And that something is 4 over 3. Minus, same thing, integral of x to the power 3 over 2 is x to the power 5 over 2, and 2 over 5 times 5 over 2 will give us the one that's in front. And proceeding in this manner, we get 2 over 3 times x cubed, derivative of that term, and finally plus 1 over 4 times x to the power 4, integrated from 0 to 1. So it's a simple match to substitute 1 wherever you see x, and when you do that, you'll just get 4 over 3 minus 2 over 5 minus 2 over 3 plus 1 over 4. And doing this basic addition and subtraction of fractions, you will see that the answer is 31 over 60. So the left-hand side of Green's theorem is basically 31 over 60. So if you evaluate the right-hand side, we should get the same answer. So let's just do that. So what we're evaluating is the line integral around a closed path of p dx plus q dy, and this is equal to the area along the closed path of our components of the vector. So let's just remind ourselves what the components of the vector are in the problem. And it was given to us as xy times I hat and 2x minus y as the j component. So when we put these things in, what we're evaluating is xy dx, that's what p was, then plus 2x minus y dy, and evaluate this line integral. So since this is along a closed path, we need to specify our direction and our various curves and all of these things. So you recall that we had split our two paths to be C1 and C2. C1 represented y is equal to x squared, and C2 represented y is equal to the square root of x. So we evaluate the line integral from O to P, that's along C1, and then we evaluate the line integral from P back to O. So that will give us the area around this closed path. So let's do that. So what we'll do is we'll call the integral along C1 to be I1 and the integral along C2 to be I2. So I1 is the integral along C1, okay? And you could see that for C1, it goes from 0 to 1 as the curve. So that's what we're going to integrate. And then C2 goes from 1 to 0. So I1 is the integral from 0 to 1 of xy dx plus 2x minus y dy. And of course, we know from the curve that this first part, C1, corresponds to y is equal to x squared. And of course, dy is equal to 2x dx. So substituting all of those things, we get the integral from 0 to 1 of x times x squared dx, that's this first term, plus 2x minus y, and y is x squared, and dy is just 2x dx. So it's times 2x dx. And simplifying all of this, we get the integral from 0 to 1 of x cubed. So multiplying this out, we get 4x squared minus 2x cubed dx. So proceeding to evaluate this integral, what we get is x cubed, which is integrated to become 1 over 4 x to the power 4. Then carrying on in this manner, we get plus 4 over 3 x cubed, which is the second term integrated, and then lastly minus half x to the power 4 integrated from 0 to 1. So that becomes 1 over 4 plus 4 over 3 minus a half, which gives us 13 over 12. So that is what I1 is equal to. So now we will do the same for I2. And remember that I2 is being integrated along C2. So we're going back from P to O. So we're integrating from 1 to 0. And the curve is y is equal to the square root of x. So let's just go down here. So I2 is going to equal to the integral from 1 to 0, but we're not really going to integrate from 1 to 0. We're just going to reverse the order of integration and put a negative in front. It's the same thing. And writing the rest of it out, so it's going to be, the first term was xy. We can see it here. So it's xy, and y is equal to the square root of x. So I'll just write that along the side. So y is equal to the square root of x. Therefore, dy is also equal to half x to the minus half dx. So we find the derivative of that. So anyway, computing this line integral, so we have xy, and y is the square root of x. So it's x to the power half dx, and then substituting the rest, we have 2x minus y, and y is the square root of x. And dy we just showed to be half x to the minus half dx. So we substitute that in. We're multiplying by half times x to the power minus half dx. Simplifying that, what we get is the integral from 0 to 1 of x to the power 3 over 2, that's 1 plus a half, plus now we have a half times 2, which is just 1, and x to the power 1 times x to the minus half. So 1 minus a half gives us a half. So this term becomes x to the power half. And lastly, we have x to the power half times x to the minus half. So a half times half minus a half gives us 0. So we have half x to the power 0, half x to the power 0. So that just becomes a half. So we have to minus a half. Just that term times that term. So that's dx. And we can integrate this quite easily. So that's minus, and the integral of x to the power 3 over 2 is x to the power 5 over 2 times 2 over 5. Then plus 2 over 3 times x to the power 3 over 2. That's the integral of the second term. And the last term is just a half x minus a half x, integrated from 0 to 1. And that just gives us minus 2 over 5, minus 2 over 3, and plus a half when we substitute 1 in. And then if we compute this fraction, what we see that is we get minus 17 over 30. So this was I2, and I1 was 13 over 12. So this line integral around both curves, so this line integral from pdx plus qdy, that's equal to now the I1 plus I2. So that's equal to I1 we saw was 13 over 12, and I2 was minus 17 over 30. So we have 13 over 12 minus 17 over 30, and that gives us 31 over 60 when we compute this fractions. So that's the right-hand side of Green's theorem. So if we go all the way to the top, we had saw that when we computed this double integral, it gave us the value of 31 over 60. And also this is what the right-hand side of Green's theorem has also given us. So this is just an indicator of finding out. So it could have been the case that maybe the question asked, what is the line integral around this closed path? And in this instance, perhaps it's arguable that it was easier to compute this double integral on the left-hand side than it was to do for the line integral on the right-hand side. So there might be an instance where if we wanted to compute either of these things, we might find that Green's theorem or Stoke's theorem or the divergence theorem actually allows us to compute an easier integral. So in that instance, we just have to use our judgment. So just to summarize once more, Green's theorem says that if we have a vector with two components, we find the derivatives of those components, day q dx, day p dy, we subtract them, find the double integral around the region, and we see that it's the same as merely taking the line integral around the boundary of the region. So thank you very much for watching. This ends this series on multivariable calculus.